This video is about a few operational notes on using tension that has to do with ropes and things like that in problems, and also how the signs of objects that are linked by these ropes will be set. Signs, of course, are plus and minus signs that refer to the direction of motion. It differs a little bit in some things that we've discussed before, so let's just get right into it and see what we're talking about here. So first thing on tension, I just want to list three things about tension that you have to remember. This can be very important for these types of problems that we're going to be working on. The first one is, I think we mentioned before in another video, that T always pulls away from its point of contact. That means that whenever a rope is tied on an object, the rope will always pull on the object, never push on it. There's sort of a fun colloquialism you can find on t-shirts and on the internet and things like this. And it says things like, you can't push on a rope. And that's basically true. So if you have like a ground like this and there's an object like this sitting on the ground and you have a rope attached to it, I think we all sort of know that if you were a person standing here wanting to interact with this object somehow by using this rope, you would not push on the rope that way. What would happen if you did that is the rope would just sort of go limp and fall onto the floor. You wouldn't be able to push on the block by pushing on this rope. So that's not going to work. You always have to grab the rope and pull on it that way. You always have to make a pull on the rope like that. And of course the way that'll translate is there's another video that discusses how force can be transmitted through a rope via the tension here. And so as you pull on the rope on this end, all the little molecules get pulled on, and the result is that there's going to be a net pull on the block this way because of the rope. But notice that this interaction right here between the rope and the object in there is always a pull away. It's never a push toward, it always pulls away. So there's the first thing about tension to know or remember. The second thing about tension has to do with this issue of the plus and minus signs. So I'll just sort of label this item here, T and the plus minus signs. Sort of works like this. It turns out that the rule that you can sort of remember this is that T on opposite ends of a rope have opposite signs. Have opposite signs. Very important to remember that. So remember that the plus and minus sign dictates the direction of force might be acting on. And so all I'm saying in this sort of rule here is that if you have a tension on opposite ends of a rope or a cable or a wire, whatever happens to be in the problem, those tension will have opposite signs. And here's just a couple examples, and we'll see more when we get into some actual problems on this. But for instance, if say you have a ground like this, and you have a block like this and a block like this, and they're tied together with a rope here, we can say that the tension in this rope is, say, T1, and say someone's pulling on this rope with a force. So it really isn't important exactly what's happening, but you can imagine a person here pulling on this block. Since these two blocks are linked or tied by rope, then both blocks are sort of going to drag along as well. And so that's part of what we said here in the title here. We're talking about tension and these so-called linked objects, because when you think about it, that's what ropes do. They sort of link objects together in their motion. Okay, so there we go. So what would happen here is, well, the first thing you could do is you can use this first idea that we put out, that tensions always pull away from objects. And so there'll be a tension T1 in this rope right here, and without really knowing any of the dynamics of the problem here, since tensions always pull, there'll definitely be a T1 pulling rightwards on this block. What about the other end? Well, ropes always pull away from the points of contact, so there'll definitely be a T1 in that rope pulling away as well, something like that. So ropes always pull away from the points of contact. I've done that here. And also, since the rope is massless, the tension throughout the rope is going to be the same. And so this number 2 here, we'll come back with another example in a second. That leads to our sort of third thing about tension here, is that if you have a massless rope, which we do in all the problems we're going to be working, at least in this class here, you can say that T is the same throughout the rope. Because I misspelled throughout there. Throughout the rope. So if it's a massless rope, tension will be the same. So here's this massless rope, which is linking these two objects in here. It's T1 in the rope. And so on one end there'll be a T1, on the other end there'll be a T1. That's always going to be the same. We've drawn the tension pulling away from both points of contact in there. And furthermore, on this last point I'm saying about the signs of the tensions, now you're free to start choosing some signs. So because we have to get the directionality going here. Okay, because if this force is to the right, we might be most natural for us to call that a positive, because we're used to our Cartesian coordinate system where right is positive and left is negative. But if this is going to be positive this way, this tension, because it's pulling on this block, is to the left. this is going to have a minus sign in front of it. That's going to be a minus tension, and this tension on this block here is going to be positive like that. So that's what we mean, though, by tension on opposite ends of the rope have opposite signs. This is the same rope in here, this black rope here, which I've covered with 2 red arrows, the same rope in there, but this tension on one end, this tension on the other end, they're going to have opposite signs. Let me just put up a couple more examples of that so you can sort of see how that works. I'll just sort of do it between the rule here. Here's another system right here. It's the Atwood machine, which will come up. And there's a hanging mass here and a hanging mass here over a pulley. We can call that mass 1 and we can call that mass 2. So it's the same rope, so it'll have the same tension in it. So what I'll do is tension those pull away from the points of contact, so there'll be a T pulling up on mass 1, but there'll also be a T pulling up on mass 2. I did not call it T1 and T2 because it's the same rope going over the pulley. The rope sort of extends up like this, around the pulley, and down again. It's the same rope. And so because it's a massless rope, the same tension will exist throughout the rope, so I have a T there and a T there. Again, I did not call it T1 and T2. If we wanted to assign the signs now in this problem, we could say something like this. These tensions are on opposite ends of the rope, so they have to have opposite signs. So if you're going to choose this tension over here, say, to be positive, this tension over here will be negative. So there's your positive and negative tensions on those 2 ropes there. But now what you see is sort of an interesting case, since you've chosen this sign here to be positive and this sign here to be negative. What that means is if you wanted to now assign a sign to the weight on M1 over here, the weight is still acting down. Weight always acts down. The M1 and the G always acts down, but because tension is up and positive over here, this weight will be negative over here, which is what you might expect. Now the surprise might come over here because this tension over here, this is a minus T pulling up on this block right here. This also has a weight going down, M2 times G, but because tension is negative and up over here, this weight is actually going to be positive over here. So if you look at this mass right here, this tension is up and positive, this weight is down and negative. On this mass, this tension is up but negative, and this weight is down but positive. Now that's probably the first time you've sort of put in a positive weight for something, but that's just the name of the game. Why is that so important? Well, let's just draw it one more time and then we can wrap up the video and see if we can understand exactly why it's happening this way. So here's the Atwood machine once again. Here's the 2 blocks like this here. So this is an M1 and this is an M2. So here is an M2G and here's a T up. We call this positive and that negative. Here's a T up over here again. If this is a positive, negative T over here, this has to be a positive T on this side. Opposite ends of the rope have opposite signs on the tension. And this is also going to be a minus M1G. There's its weight down like that. Here's the way the sign convention works. If, say, M2 is the heavier mass and the system is at rest, you might expect that the pulleys are going to turn clockwise. M2 will go down and M1 will go up. Is that consistent with the motion? Well, yeah, because if M2 goes down, that's the positive direction. But because of the way the pulley works, if M2 goes down, M1 must go up. So if M2 is going in the positive direction down, looks like M1 will also go in the positive direction, which is up. So see, the sign convention there is nice and consistent. Likewise, suppose the pulley was turning this way and M1 was the one going down like that. M1 would be moving in the negative direction because it's moving down, but because of the pulley, if M1 goes down, M2 must go up. So if M1 is going down in the negative direction, M2 must go up. That's also the minus direction because of the way you have the minus sign label on the tension. So the sign convention is nice and consistent in there, and that's the way we do it like that.